So good evening, everyone. I welcome you all to the second talk of STEM's 2022 lecture series. Today we have Professor Shandera with us. Before we begin the talk, let me give you a brief introduction about her. Professor Sarah is an associate professor of physics at the Eberly College of Science of the Pennsylvania State University and also a member of the American Physical Society. Her research interests are mainly in particle astrophysics, gravitational physics, cosmology, and the particles and fields. She is also the visiting fellow at the Perimeter Institute since 2015. Professor Shara is also a faculty assistant for Physics and Astronomy Women group at the Penn State University. Today, she will be delivering a talk on how gravity helps us in knowing about the dark matter with whom we can't interact directly. So before we begin, just a couple of quick remarks. It would be really great if people can turn on their videos so we can reach closer to a live interaction. And also, if you have any questions, feel free to put them in the chat and the moderators will take it to the professor. And if you want to ask directly, you can also unmute yourself and ask. So without further delay, I invite Professor Sarah for the talk. I hope all of you enjoyed the talk. Professor Sarah.
Great, thank you so much. I'm so honored and pleased to be here. I think your event is just absolutely wonderful, and I'm really happy to participate. So I'm going to tell you about a story of gravity as a chemist, which is not something that I ever thought I would say until a few years ago. So let me explain what I mean. So, one of the truly amazing pleasures of life on this planet is looking up at the sky. I've never seen a sky quite like this, but even so, looking up at everything that's out there, you feel small, you feel humble, you feel curious. And you might say to yourself, I'm going to need a bigger telescope. And here's a beautiful telescope. This is the Hubble Space Telescope. And of course, what Hubble sees is absolutely astonishing, even astonishing by the standards of how amazed you feel looking up at the sky. Because what Hubble sees is this. This is the Hubble Ultra Deep Field. And this is a very long exposure. But what you can see if you stare at that is that there is just an astonishing structure out there. And if you look a little closer, you see that those little pinpricks of light are enormously complex galaxies. And then you realize that even our Milky Way feels small and humble when it looks out at the sky. The even more amazing thing is that, that's what Hubble sees by collecting light. That's the same as the light that can reach our eyes. And, what we know is that that's not the only way to observe the universe. In fact, it's a tiny, tiny, tiny part of the way to observe the universe, even if you just look at electromagnetic radiation. So over here on the right, I've put, a spectrum of radiation, which is given to us by NASA, put together by NASA. And, you're familiar with all the other kinds of electromagnetic radiation that, power your radio or do security scanners and at the airport. And so you can see that there's a change in frequency as you go along this spectrum. And so a lot of what we do when we look out at the sky now is to look at other parts of this spectrum. So this is another NASA graphic. And I like this one because it tells you a couple really interesting things. The first one that's pretty obvious, I guess, is if you look here in the visible, you see that that's the light that gets through Earth's atmosphere. I mean, that's the whole reason that that's the light we see, right? Because we evolved here on Earth. And the stuff that doesn't get through the atmosphere is stuff we don't see very, very easily. So we don't see in the microwave, the infrared, and we don't see these high energies, which are sort of grouped into these categories up here. And you can see sort of the wavelength scale here in the middle of the image. You can see the frequency right here, but the one I want to focus on is what's at the bottom, the temperature. And you can see that stuff that's down here in the radio, the microwave, this is cold. And stuff that's up here, the UV, the X-ray, the gamma, this is emitted by stuff that's really hot. So when we look out at the universe, if we only look in visible light, we're limiting ourselves to a pretty small range of temperatures. So people pretty quickly figured out that they should go and they should look at that other light and they would see some other stuff. So here I'm showing you an object. This is the Coma Cluster. It's a very famous object in terms of dark matter studies. And it's called a cluster because it consists of a whole bunch of different galaxies. So, again, each of those dots, these are really galaxies. And, they're in a group. Basically, they're sort of gravitationally bound. If you look at their motion, they're not just, randomly flying apart or anything like that. They're really forming a gravitationally bound system. If you look in the optical, this is an optical image. This is from the Sloan Digital Sky Survey. You see the stars. You see starlight. But if you look in a different band, if you look at some of the radiation that's coming, for example, from stuff that's higher temperature, you would see, for example, this X-ray image. So, and you see it doesn't look much like the image on the other side, right? Where most of the hot gas is not distributed in the same way as the stars. So you get some idea, again, that there's actually a big object there, which isn't as obvious maybe from the optical image. And all of this gas is sort of collected with this really dense part in the middle. If you put those images on top of each other, you get this. And so then you can really see the difference in distribution between where the bright stuff is, the galaxies that are full of stars, and this hot gas, which is in the middle where you don't find stars. Okay, so before I'll come back to Coma in a second, but when we look out at the universe and we look in all of these wave bands and we look with more and more and more powerful instruments so that we get the light that's fainter and stuff that's farther away, which really is, looking back in time, right? Because the light has to travel, take some time to travel to get to us. So let me not say all the light, but let me say all the electromagnetic radiation, be a little fancier. We've mapped out what we know about the universe so far. So the image that you're seeing is an image made by the team of the WMAP satellite. This was a satellite that was mapped the cosmic microwave background. So microwave, right? You know what the wavelength of that radiation is. And what you see is the satellite over here on the far right of the image, and you see it sort of looking through this back in time if you go back toward the left. And you see two things in that picture. You see that overall envelope of the image, and that's giving you some idea about the overall expansion history of the universe. So the universe is not a static thing in any way. It's evolving and changing with time, and it's expanding. And more recently, it's expanding at an accelerated rate, and that's this sort of change in curvature here. And way back at the beginning, there was maybe this really big period of accelerated expansion very early on. But then you see also in the middle, what makes sort of this whole picture really interesting, which is the structure, right? This evolution from here where things look pretty empty, you don't see any starlight shining, and then all of a sudden stars turn on. So these are the first stars, and you see an evolution toward these really complicated structures that we see today. So understanding, why this picture looks the way that it does is what cosmologists do, and because as you go back in time here, things get hotter and denser, and because you have very high energy interactions happening in these complex objects at later times, this is also a picture that's of great interest to people who do particle theory. Because if you want to figure out what the particle physics is beyond the standard model, it turns out the universe is an incredibly rich place to do that in. Okay, so this is sort of what I just said, but the basics of this picture are that as we look out at the universe, we realize that at early times, when it started, sort of, it was very hot, it was very dense, and it was very, very smooth. So only tiny fluctuations in the density, only tiny differences in, if you like, the temperature of the photons at that time. But as things evolved, and as you get both this expansion, which is due to gravity, but locally you also get gravity clumping things together, the universe became colder because of the expansion, mostly empty, but extremely lumpy. So we have these really complex localized structures that are these amazing galaxies today. And usually when we do cosmology, we sort of separate out these two pictures. We sort of imagine smoothing the universe and smoothing out all of that structure, and just asking, if we made that sort of homogeneous, we spread it out, what does the homogeneous universe do? And that's the part where you go from sort of hot to cold, and you go from dense to nearly empty. And when you ask about that, primarily you're just asking how gravity acts when it's sourced by different kinds of matter and radiation. But on the other hand, we have the remarkable inhomogeneous universe. And so this is the regime where we're not interested in, sort of a global average temperature. We're very interested in temperature differences. We're very interested in what the lumps are doing. And on these scales, gravity, of course, is important because it's really the reason that this stuff is lumping together. But you also have really important effects from particle physics and nuclear physics, and you have all kinds of reasons that this stuff is radiating light and other particles, spewing other particles out into the universe. And it's also actually the regime of chemistry as well. Okay, so looking at these pictures, both this homogeneous bit and the inhomogeneous bit, they both tell us something really interesting. And that something is that there's all kinds of stuff out there, but it's not radiating. You can't see it in any of those pictures that we looked at before. So let me show you what I mean. Let's look at Coma again. So you can try to estimate how much mass there is in the Coma cluster due to stars. And this is pretty tricky. So I put a number there, but I'm really being really glib about what that number actually is, because how do you know? Well, you can only see the light. So you have to somehow figure out from the amount of light, from the spectrum of the light, right? Which colors you see more strongly, what's going on inside the stars, what are they burning, what are all the sources emitting that light. And then you have to figure out how heavy they should be, right? And that's sort of a chemistry problem right there, but you can do it, you can estimate it. Oh, and you also have to decide sort of, what do you define by Coma? Where do you stop? Are you just looking at a little bit or more? Where do you stop? So you get different numbers depending on what you do. Okay, but you get a number. But then let's go back and remember that we had all of that hot gas. And so let's go and try to estimate how much mass there is in gas. And again, how do you do it? Well, you know something about the temperature of light that's coming off. And so you can try to figure out what's the density of the gas and what's the total mass based on what kind of particles are in the gas. Yes, is there a question?
No, not yet.
Okay.
Cecily, please do type in the chat.
Okay. And so you can go and estimate that. And again, the number that you get depends on exactly what you do and what size, what radius you consider the gas inside. But what you find out is that there's more. So, if there were, something like 10 to the 14 solar masses in stars, there's 3 or maybe 10 times 10 to the 14 solar masses worth of stuff in the gas. Okay, so cool. Well, we're physicists. We like to, do things multiple ways, and all this stuff about gas and chemistry and light, that sounds pretty complicated. So what if we just use kinematics? If we use kinematics, what do we find in terms of the mass of the Coma cluster? And this is actually a really old idea. It's an idea that dates back to the 1930s and is credited to Fritz Zwicky. And Zwicky, in fact, tried to do this. So what do we mean by using kinematics? Well, actually, it's pretty easy. Let's just assume that there's some big mass there, and it appears, at least from those pictures, that maybe there's some sort of center that we can think of. And we think this thing is gravitationally bound. And what does that mean? Well, it means that those different objects are going around in circles, basically. Not really circles, but let's approximate them as circles. So if they're going around in circles and we measure how fast they're going on those orbits, and we know that there's force, right? The whole reason that they're going around on orbits is because this thing is gravitationally bound. So there should be a force. And so we can just use our simple equations of motion that the acceleration, right, that keeps this thing moving on its orbit is given by v squared over r. R is the radius out from the center. V is that circular velocity. And this is gravity, right? The reason stuff is in orbits is because of gravity. So we know that the acceleration should be Newton's constant. Then the mass, the total mass that's responsible for this motion over r squared. And if you just put those equations together, then you find that you expect that the velocity should not be the same at every distance out from the center of this object, but it should go as 1 over r. And of course, if you measure those velocities and they all go as 1 over r, they should all provide you measures of the total mass in the galaxy. So what do you actually see? So people have done this for many, many, many years. These are called rotation curves. And what you see on the y-axis is a plot of the measured circular velocity. And what you see on the x-axis is a radius. So you look at different objects, you look at them, at different distances out from the center, and you try to measure their velocities, and you put it all on a plot. And the scale here is kiloparsecs, so maybe that doesn't mean a lot. But where we sit is, maybe 8.5 kiloparsecs from the center of our galaxy. And And you can see that in this particular case, the extent of a typical galaxy is somewhere out to here. Okay, so you see the data up here. That's these little points here. And as you can imagine, it's actually pretty hard to measure these velocities, right? Because you want to look at change in the spectra, but people do it. They do an amazing job. This is an old plot, but I like it because it's just pretty clear. And what you see in these straight lines are, what was your expectation? You can do those other calculations. You can say, oh, we see all these stars. Let's try to figure out where the stars are and how much, they're contributing to this gravitational potential. And this solid line that's labeled disk, right? Because the galaxies are sort of in a disk, and the stars lie in that disk. That's the expectation of what this curve would look like if all of this acceleration, this radial motion, was coming from stars. But that's not at all what it looks like, right? It doesn't go down as 1 over r. It actually has this kind of shallow, almost flat slope here. And so you can say that what you're missing is some other source of matter. And you can just figure out how much matter you have to add as a function of radius to what you measure in the stars and the gas, and actually get the curve that you see. And that's this line labeled halo. So there's something there, and it's called halo because there's not really much here right in the middle. You notice that at least in this picture, what they've added is more important out here. We can talk about that later, but in this picture, it looks like it's this halo. So when you add those things together, you get something that explains the data. But what is that stuff? How much is it? How much did we have to add? I mean, you can already see from the picture you had to add quite a bit. That's one example of a rotation curve, and this idea that Fritz Zwicky did, he didn't make a complicated, as nice a plot as that, but he still thought there was something there. But it wasn't until people could go, and measure many, 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 many examples of these types of rotation curves that we started to really understand that systematically there's something going on in all of the galaxies that we don't understand. And this is a great picture of Vera Rubin at her telescope. And it's really, she was responsible for many, many of the rotation curves that are considered to have confirmed the idea of dark matter. So why are we saying that? Well, let's just see how much is there. And again, let's look at Coma, and this is the one that Fritz Zwicky estimated long, long ago. You think you've got a few times 10 to the 14 solar masses in there. If you look at the kinematics, though, you say, whoa, there is way, way, way more matter than that. Maybe as much as almost an order of magnitude more matter. And the thing of it is, yeah, go ahead.
Yeah, so there are some questions I think I will take. So there's one question that how is the expected mass with respect to the radius is generated?
How is which one generated? The
expected mass with respect to radius.
Oh, good. So this curve here, I said it expected. Yeah. So you can sort of do what we talked about, on the previous slide. You take measurements at different, you look at all the objects, let's say, and all the gas that you can see, and you use your knowledge of, particle physics and chemistry to figure out how the radiation that you see, right, the temperature that it's at, say, and the intensity of it, what that tells you about the kind of object that's emitting that light. And then you can estimate what the mass is. So if it's a star, for example, whether it's a big puffy star, and it's an old star that kind of ran out of fuel, compared to if it's a really hot new star that's got a lot of fuel and it's burning really brightly, you can try to figure out what the mass of the stars must be. And similarly for the hot gas. So you go and make measurements, and they're not showing you any of that data here. You go and make measurements of what you can see and estimate how much mass is there. And it's a little bit deceptive maybe because of course they don't actually know that as like a perfectly smooth line, right? There's some uncertainty there too. But the overall upshot is that stuff, you do see a concentration of gas and stars that's pretty localized, and that can't be the actual edge of the mass. There has to be more mass that's extending out here to match this data. I don't know if that answered your question. If it didn't, feel free to ask again. Anything else?
I think that answers. So there's another question. So it is from Siddhant. Do we add the effects of both the halo and the disk, and then try to find the compensation term?
Yeah, great. Yeah, thanks. Thanks so much for these questions. It's really great to feel like I'm not just talking at my screen. So I think that's exactly what they've done here is they've, mapped out, and again, it's deceptive because these lines look the same, but they mapped out what they expect to see from the stuff they can measure. And then they've sort of added this compensating bit that they're calling the halo. And in order to get a line here that actually goes through the data. So you can consider this stuff to be data, this curve to be data and modeling, and then this halo is really the modeling part that they just say, okay, this must be what we need if the motion that we're seeing follows, those simple kinematic laws of gravity.
Yeah. Thank you.
Okay, thanks. Good, yeah, and I've talked about this stuff so much that it's easier for me to say things that probably aren't clear. So I really appreciate it if you stop me. All right. Okay, so there's a ton of stuff there, right? And if you quantify it, in a way that's not just that curve, you can see that in fact, an enormous fraction, maybe 85%, maybe 95% of the matter that has to be there for those rotation curves to make sense, can't be in the stars and it can't be in the gas. And in fact, you can go and look across that electromagnetic spectrum and you won't see any electromagnetic radiation that tells you that this matter is there. So that's why, in fact, it's called dark matter, because it doesn't radiate. So here's our standard model. This is the very cuddly version of the standard model, which you can get these elementary particles as little stuffed particles. We're very proud of it. We've worked really hard to figure out what it is. We built these amazing colliders. We found the Higgs boson. We're very proud. And we look out at the universe, and once again, we're humbled, right? Because what we know all about, and we've worked so hard to figure out, it's outnumbered by an enormous amount by stuff that we have no idea what it is. And I explained to you the rotation curve idea, and you might say, oh, well, maybe your law of gravity is wrong, or maybe you just didn't look hard enough. There are lots of reasons you might think, oh, maybe the explanation that there's a bunch of matter there is wrong. But if you think back to that picture of the evolution of the universe and all of the sort of data points we have in the history of that was shown in the history there, we have many, 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 many lines of evidence that in fact it's true. About 85% of the matter is dark matter. Yeah, sorry, is there a question?
Excuse me, ma'am.
Yeah.
I had a question. Why does that previous data curve indicate that something is missing? I mean, it could indicate that our calculation or our methods are wrong and that we need to change our methods. Maybe, I mean, this could also be a possibility.
Good. Yeah, I'm glad you brought that up. And that's why, in some ways, now that I think about it, I wish I had a different graph, because you can see the measurement error here in the data about the rotation. And if those error bars are honest, they both include, really the sort of crudeness of the measurement, but also uncertainties, that make it hard to determine what the velocity actually is. What I wish this plot showed is the uncertainty in this calculation of where the matter is in the disk. And because then you might be more convinced, but absolutely, you're right. And these kind of measurements have been done since the 1960s, and they've now been done on zillions of galaxies. And not all of the rotation curves look exactly like this, but there's very, very, very strong evidence that even given all of the uncertainties in modeling, and even given the difficulty of making the observations, that there are in fact halos of matter that doesn't emit electromagnetic radiation present in the galaxies. But thank you for bringing that up.
Ma'am?
Yep.
Shubham, your voice isn't clear. Could you just type your question in the chat? He'll type the question.
Okay, super. Do you want me to wait? I'll wait for a second.
Or if it's a bit too long of it, yeah, he's texted. Maybe the laws we are familiar with are not correct.
Yeah, great, good. So this is another thing. Good, you guys are wonderful. This is another thing that people have absolutely thought about. Maybe we've just got the wrong law. And you can imagine that if this is the only kind of data that you've got, indeed, it's possible to just say, oh, well, you know what? I've discovered a new law of gravity that's operative in these, galaxy scale objects. And you can write down that law. But the thing is, this isn't the only data that we've got. So, if we look out again at the sort of overall expansion history picture, that's another type of data that tells us very strongly, in fact, doesn't suggest, it tells us that there's something that acts like matter in the sense that it doesn't act like radiation, that has to be present to explain what we see in the expansion history. So that we measure, by looking, for example, at the rates at which things are moving away from each other, things that aren't gravitationally bound. And there are other things about sort of the time evolution of that picture, right? Galaxies didn't just appear and we don't just see them as these objects for all time. We know that we started out with sort of very small differences in density, and those things gravitationally evolved over time to sort of collect together the matter into, these things that are the galaxies and the clusters of galaxies. And when we look at the dynamics of how that happened, and everything about the standard model, we can calculate exactly. We know exactly how it should behave. Again, we find that we need some sort of matter that explains how these gravitational potential wells started growing in a way that doesn't work if you just include standard model. So the upshot is, once you put all of that together, people still try. They still try to have modifications of the laws of gravity that make that work. But there's no modification that's proposed that works with all of the data. So I would say, the evidence is very, 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 very strong that really what's out there is just some kind of matter that doesn't emit electromagnetic light. Okay, cool. So our poor little particle zoo is maybe not quite as proud as it once was. Okay, so if we indeed go through the exercise that you all just took us through and we say, okay, are we really sure our measurements are right? Yeah, we're pretty sure. Okay, maybe we have the dynamics wrong. Let's look at some other types of observation with different dynamics. Do we really have the dynamics right? Yeah, everything seems to fit the dynamics. Then we're left with this puzzle of, okay, so we've got some particles there. What are they? They certainly seem to interact gravitationally, but is this one particle? Is it a bunch of fundamental particles? Is it not a particle at all, but a bunch of little black holes or something? And how are we going to solve that? Well, if those particles interact with our particles, then we've got a pretty good set of solutions, right? Because we can just go out and build detectors that try to look for those particles. So let's assume that. Let's start there. That seems really normal. Let's assume that even though it doesn't emit light, so it must not interact too strongly, right? That limits how it can interact if it's not light emitting. Maybe we can still find a way that it interacts with the standard model, and we can go and look for it. So how are we going to do it? Well, maybe we can just make some, right? That'd be great. If we could just make it, then we'd solve the problem. So let's try that. And so step one of this program is dig a hole. Okay, well, actually what we're going to do is we're going to dig a 27-kilometer tunnel. And inside of it, we're going to put some magnets with a beam of particles that's going to travel down here. And these are going to be protons. This is the Large Hadron Collider. And we're going to send them zipping around so they're really, really, really fast. And we're going to let them run into each other at a few different places. And we're going to put some detectors at the places where they run into each other. So the CMS, ALICE, LHCb, ATLAS, these are all different types of places where you actually measure what goes on in these particle collisions. And they have these absolutely extraordinary, to my poor theorist brain, complicated machines that are going to measure all this stuff. It's just amazing that humans can do this. And we're going to see if we can find any dark matter. So, oh yeah, I should say, if you need a musical interlude that includes physics, and you want to learn more about the LHC, if you haven't already, you should go and check out this Large Hadron wrap, which was made on some cell phones. So the picture is pretty blurry, but it's great. And you can learn more about the LHC. Okay, so we're going to make it. So if we make it, that means we have to build a detector and we have to see something in the detector where we can say, nope, that wasn't a standard model particle. That was absolutely dark matter. How's that going to work? The picture that you're seeing here from the ATLAS experiment is a picture of detections from a collision event. So you send, protons, you send particles of the standard model through, and you have them collide, and you get a really big mess because protons are not simple objects, right? They're not fundamental particles. They're particles that are made of quarks. They have interactions that have to do with the strong force, which is a messy, difficult to describe kind of thing. It's not like a simple, sort of a simple force like electromagnetism is. And you build detectors around this pipe in the place where the collision happens that are designed to capture energetic particles that fly out of this collision. And you might try to capture, some electromagnetic stuff closer in and build really heavy shielding so the heavy particles, other things that are sort of strongly interacting are detected out here. This is an example of such an event. So that's a big mess. So how are we going to find any dark matter? Did we get any? How do we know? And actually, we come back to kinematics again. And we basically say, well, if we got everything, we should have conservation of momentum, right? We know what came in. It was these colliding bunches of protons. And when we detect stuff and we measure how much energy they deposit, right, we know their direction and we know how much energy they deposit, so we can calculate their momentum. And did we find anything? Did we find everything? Do we see any missing momentum? This is a little bit more of a sketch that's of that idea that corresponds with the detector. You look at the detector and you measure a bunch of stuff, say this red stuff, and a bunch of other stuff, this green stuff, and you see these big, streams. They're called jets. These streams of sort of complex, particle structure that comes out at the edges, and you can just say, well, if I think of these as billiard balls, that can't be a conservation of momentum story there, right? They're both going sort of toward the right. So there must be something else that's going sort of toward the left that compensates. And this is the missing transverse energy. Transverse because, this picture is in the plane of the collision. And it's invisible. We didn't see it. So there must be something there that didn't interact very strongly with our detectors, which after all are made of standard model particles, that we didn't see. And so if you see some energy that you can't account for, that would be a sign of a particle that you can't account for. That's a new particle. And this, if you want to read a little bit more about this, you can look, for example, at this nice blog post. It's from a few years ago, but it's nice. You get the idea. And here's the author. So we do this, we measure, we say, oh, did we get any dark matter? And we say, not yet. Okay, so that didn't work. Okay, well, maybe it's really hard to make, but we know it's out there. We just said that if our observations are right, there's a whole bunch of dark matter out there in the universe. Maybe what we should do is build a detector where we wait for dark matter particles to come zipping by and hit the stuff in our detector. We don't have to make it. Let's just look again for it to hit something that we do make. How do we do that? Well, first you dig a hole. Okay. In this case, we're going to go down into a mine and we're going to put a detector down there. And that just sort of makes a cleaner environment because, all kinds of stuff comes zipping in from high energy events out there in the universe. And a lot of that stuff isn't dark matter. Maybe it's really high energy, protons produced in high energy events, that have to do with stars that are super active. And we don't want that. What we want is dark matter. So most of that stuff that comes in, it's standard model stuff. It's going to be sort of shielded by the Earth because it interacts with all the standard model stuff that's in the Earth. Dark matter is very weakly interacting, so it's not going to be shielded by the Earth. So let's put our detector down there and hope that mostly only dark matter comes through. And so if we see something, we can hopefully figure out that it's dark matter. So I'm going to talk a little bit. This is one of the sort of modern detectors, LZ. Lux was the large underground xenon experiment, and there didn't see anything. So we're increasing to the next level, and this is an experiment that will run. And what's the idea? Well, the idea is that and here I've showed a cartoon, and here you can see something produced by the collaboration. A dark matter particle comes zipping in from out there in the universe, and it hits the stuff in the tank. And the stuff in the tank is really simple. We understand the stuff in the tank. It's xenon, so it's inert, it's heavy, and on the other hand, if one of these particles gets hit and sort of jostles around all of this bunch of xenon, then that jostling is going to produce some electrons that fly up, and electrons are really easy to detect. And the dark matter is just going to scatter again like a billiard ball and go off and out. But we're going to see kinematically the fact that it bumped into our xenon through the signal that it produces with electrons. So we're back to kinematics again. Okay.
So there are some questions at this time.
Great.
So there is one question by Advay that can't the dark matter be other small yet heavy bodies, such as clusters of very small black holes, with not very bright acceleration disk or etc. like that?
Yeah. So good. Okay. So there's definitely a difference if you consider that instead of being a particle, dark matter is sort of let's call it a macroscopic object, like a whole bunch of black holes. And, well, okay, let me say two things. Let me first say, your idea of how many dark matter particles are going to pass through the Earth and with what velocity comes from making measurements, again, of kinematics where you can estimate the density of dark matter, as a function of distance out from, say, the center of the galaxy. And you also can estimate its velocity, right? And again, it's sort of that same idea that there's a gravitational potential, stuff is zipping around. And if there's no chemistry, you know exactly how fast it's zipping around, right? So for dark matter, if there's nothing fancy going on, that zipping around is, again, just kinematics. So, these experiments, when they set their limits, rely on inferred, from the dynamics of galaxies, inferred estimates of how much dark matter there is out there and what velocity it's moving at. So those things, there are certain bounds on those things, no matter what the dark matter is made out of. But what if it is something like black holes? Isn't that a completely different story? And it is a different story. And most of that, if you want to talk that through, and we can certainly spend more time on it, although I think I'd prefer to do it at the end, you need to ask yourself, where did those things come from? And can we distinguish dark matter that's made of these macroscopic things, again, by the dynamics, compared to dark matter that's some sort of particle physics, again, by the fact that this stuff will interact differently with all the other matter that's out there than something that just interacts gravitationally well. So that's a great question, and we can definitely come back to it at the end. Anything else, actually, while we're stopped?
Yeah, so there's one question that in the strategy one, when you said that we can create it in the lab, so how can we show that we created the exact same thing that you wanted?
Oh, great. Yeah, good. Very good. So in fact, as you probably know, when we build these accelerators, we're hoping to see lots of stuff, new physics, right? And people have lots of ideas for the particles that could be there. And it certainly could be the case that there are actually lots of particles that are new and that interact with the standard model, but they don't have to be the dark matter. And how do you know? Well, once you know what the interaction is, you sort of go back to that whole cosmological picture where, as I said a few minutes ago, gravitationally how much dark matter there has to be, and sort of when it started to be able to form these potential wells that the standard model stuff could fall into. And so you can go back and you can say, if what we detected a new particle, it interacts in this way with the standard model, let's go back and recalculate all of our cosmology. And see how much of these particles should be there, what their interactions are, so we know if they're being, if they're annihilating, if they're being created, and how they're gravitating, because things that are zipping around that are relativistic, they are less able to clump than stuff that's kind of cold and slow and that just can fall in gravitationally. So you go back and you look at that whole story and you say, is it consistent that what we saw in the collider could be actually responsible for the dark matter? And so that's an enormous field where people do all kinds of calculations to check those things out. Yeah, good.
Yeah, thank you.
Yep. And of course, it'd be more fun if we had seen anything in those colliders that's really new. But aside from a few maybes, we haven't. Okay. Whoops, no. Let's see. So yeah, so maybe I was done with this. So again, these are really amazing experiments, and they were designed to go after, kind of connecting to what we just said, some examples of dark matter particles that seemed really natural. If you sort of took that cosmological history and you said, oh, what would be sort of a natural way that you might, what might be a natural mass, what might be a natural interaction of these particles with the standard model to account for the dark matter, particles that you would observe in this kind of detector were a very natural candidate. So it's been sort of, I don't know, frustrating. It's been exciting, on the other hand, that these detectors haven't seen anything. So did we get any dark matter? Not yet. Okay. So then you say, well, okay, look, I'm not finding it in my detectors. But on the other hand, there's all kinds of stuff out there. And even though my collider, I'm very proud of it because I zip stuff around at high energies, I realize that processes that happen out there in the universe happen at extraordinarily high energies, right? The sort of energy engines that you can generate inside of very massive stars are really extraordinary, very high energy events. So let's look up, and maybe what we'll see is that there's some evidence that there is dark matter out there, and it has some collisions, and because it interacts with the standard model, sometimes you get standard model stuff out of those collisions. And standard model stuff in general produces light. So if we look up for unexpected light, It's not going to be coming directly from the dark matter, but it's coming kind of indirectly through a bunch of processes where dark matter couples to standard model, and standard model eventually emits light. So you need a telescope. This is my daughter's favorite learn how to draw site. So you can go and figure out how to draw a telescope there. And you look up, and you should look somewhere where you expect there to be lots of dark matter and lots of really exciting high energy events. So you might want to look, for example, toward the center of the galaxy. And the telescope, one of the telescopes that does this is the Fermi satellite, and it's actually a satellite. It's not down on the ground, and it does exactly that. It looks for very high energy light, gamma rays, coming from, say, the center of the galaxy. Super interesting for astrophysics, but also potentially a way to look for dark matter if you see something that you can't otherwise explain. And the idea here again is that there's some dark matter. We don't know what it is. It collides and produces something else, which is probably, some mixture of dark stuff and standard model stuff. And eventually that standard model stuff, in this complex environment, radiates out some particles that we can actually detect. Maybe it radiates out some really fast moving neutrinos, some, electrons and positrons, or some photons. And again, people build, very specific models where all of these little blobs and arrows are filled in, and you can calculate exactly, the likelihood that this happens given your estimate for how much dark matter is out there in a dense environment. Okay, so what do you see? Do you get any dark matter? You say, oh, wait, there's something. Yes, go ahead.
Nothing looks like that. Seems to be a stay nice.
Okay, thanks. And it happens periodically that people get very excited because they look here toward the center of the galaxy, lots of stuff is going on, and they see something. And it doesn't correspond at the time it's observed to any known astrophysical phenomena. And then people think about it and they say, okay, what is that? What is that? And very often the answer is, oh, actually that's, just astrophysics. I mean, astrophysics is incredibly complicated stuff, right? And so you learn something new about processes in the universe. And then maybe, a couple months later, same thing happens. There's something, you say, oh, actually, that's just astrophysics. And so the answer overall is that we haven't detected any dark matter this way, definitively. So let me just summarize this for a second. This is a kind of diagram that you see very often as a summary for how you might detect dark matter. And what you see are dark matter particles over here and standard model particles over here. And if you imagine starting with standard model stuff and smashing it together and producing dark matter, that's that collider way of going about it, right? You take stuff that you can control, you know the energy of it, smash it together, see what comes out, and get some dark matter. If you think about the diagram from bottom to top, you're talking about dark matter coming in and scattering with a standard model particle. The dark matter goes out, but so does something in the standard model. So this is like those, if you hit a nucleus, a xenon atom, you might radiate off some electrons that you can detect. And if you go from left to right, that's a kind of astrophysical way of doing it, where the detection is indirect. You see sort of the radiation that's the result of complex processes that started with dark matter colliding and produced stuff that you could see at the end of the day. So this is a very typical picture for dark matter studies. And unfortunately, you say, okay, well, did we get any? And you say, not yet. Okay. Well, maybe we're stumped. We keep looking and we don't find anything. So, what if the interaction with dark matter particles is just so weak that we're never going to detect it? Or what if it actually doesn't exist? What if there is no coupling except gravitationally? Are we just doomed? Do we have to go home and cry? Is this quest totally hopeless? Oops, physics, sorry, missing S. And I think the answer is no. Okay, so at this point I have to give you a disclaimer. There are many, 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 many models of dark matter. There are many good ideas out there. You could, I don't know, fill an enormous room with all of the papers that have been written about good ideas of dark matter. When you're a theorist, you have your own ideas that you follow. And those ideas are, actually kind of like pets. Even if you don't like goldfish or snakes or cats, and you decide that you like dogs, the kind of dog that you love is going to be very different from the kind of dog that somebody else loves. And that's just how it is. It's sort of the same with theories, especially theories of, new physics. There are going to be some that you just like, yeah, I like that. That's a good idea. And there are going to be some where you're like, that's a crazy idea. Who would ever think of that? I'm not interested in that. So I'm going to tell you about an idea that I happen to think is pretty interesting. But there are lots of ideas out there. So please don't take this, as representative of all those ideas, because it's certainly not. But I think it is pretty interesting. And this is the story of gravity, the chemist. So what about gravity? So we talked about, kinematics. We talked about how things move in galaxies. We talked about how, the overall expansion of the universe goes. And that's great. Those are still indirect, in some ways, detections of gravitational forces, because what we measure is light most of the time. We measure something in the electromagnetic spectrum, and that's how we infer the kinematics, we infer the motion, and from that we infer the presence of matter. Very recently, though, we have the ability now to actually directly detect gravitational wave signals from the collision of very heavy objects. And so this is a picture from the LIGO and Virgo collaborations of all their events that they've detected recently. And what's nice about this is that it's purely gravitational, right? You don't have to have any interaction with standard model particles in order to detect this. Your detectors move, they move kinematically, they move directly because of gravity. And all of those black holes, where do they come from? Even though you're detecting them gravitationally, they're not inherently somehow pure gravity objects, right? You draw these very messy pictures about how you have one of these, the clumpiness of the universe gives you places where you can form stars. And those stars have all kinds of complex evolutions. Some of those evolutions end in the formation of things like black holes. And what's going on inside all of these processes, it's not, particle physics in the sense that it's not driven by, say, collisions between individual fundamental particles. It's something that's happening in an environment that is chemically rich. So I'd say it's really chemistry. Why chemistry? Well, these structures that are forming, if you think of them in terms of not just individual particle motions, right? An individual particle or even an individual star has a well-defined velocity, a well-defined momentum, but as an individual object, it doesn't have a well-defined temperature. Temperature is really something that comes from an ensemble of motions, right? A thermal distribution, say, of velocities. But these are regions where the temperature, the thermal processes are really important, and these become the realm of chemistry. And part of the reason is that the gravitational wells speed things up, right? There's a lot of motion going on. And if you want to form a star or a black hole, matter has to be able to be clumped together by gravity, which means that you have to be able to cool it down, right? If it's zipping around at a high velocity, it can't clump down, right? That's what's happening when something is in orbit. But if you bleed off energy, then things can collapse down. So what's happening inside of these big gas clouds is that stuff is actually cooling. And that's what allows you to form these protostars, for example, that become the black holes. And why is it cooling? Well, it's cooling because of particle processes, right? So for example, you might have some electrons, you might have some hydrogen, and maybe there's a fast electron that comes and bumps into the hydrogen. And what happens? Well, you can give some of that energy to the hydrogen atom and excite it into a state, right? A higher energy state. That's the configuration of where the electrons sit compared to the proton, say. And the electron, meanwhile, goes off with a slower velocity. So the electron has cooled if this is happening in the big distribution of stuff. The hydrogen is in this excited state, but the hydrogen atom can, the electrons can go back to the ground state and emit a photon. And the photon can escape the gas. So the hydrogen atom, right, the energy that came in from the fast electron, the electron cooled, but the hydrogen atom, got hotter in some sense. It got more energetic. But the hydrogen atom can just emit a photon, and the photon can fly away. And then the gas itself, the hydrogen and the electron, can be said to have cooled. So those are the kinds of processes that are happening. And this I'm calling chemistry because it really relies on the fact that I can make an atom, right, out of a proton and an electron and have it be a bound state. So that's chemistry. Okay, so what really matters here is that chemistry. Okay, so let's go back and just put this in context for a minute. We have this beautiful picture of the hot but dense and uniform universe, and it's cooling on large scales, but locally we have these complex structures forming where things get very hot, very dense, and produce environments where eventually you can have even something as dense as a black hole, as compact as a black hole. So, and in all of that, the dark matter is doing something, and we know what it has to do something to help create these potential wells where we get galaxies. But that picture on the last page, this is incredibly rich, right? This is actually a different picture of Coma now in different wave bands. And actually, one of the ways that we learn about particle processes is from the standard model events that we detect out there in the universe. So what if dark matter had a similarly rich spectrum of small scale structures? And this goes a little bit toward the question somebody asked me about black holes, but it's a reason why they might be there. If you have chemistry and you can cool, you can form compact structures. And what we know from understanding all of these pictures and how we make sense of all of these observations is that the details of all of this rich structure, it tells us something about the spectrum of particles that are out there, right? You can tell that there has to be something like a strong force, right, to have this nuclear fuel burning in stars. Certainly, there's an electromagnetic force that you can figure out from looking at these types of emissions. So the details of what we see for the standard model constrain the particle physics. So the same can be true of dark matter. Even if there's no non-gravitational interaction between dark matter and the standard model, we never detect it in the lab. If we know something about the spectrum of complex structures that form, do we get stars? Do we get black holes? Of course, the stars aren't going to radiate photons, they're going to radiate something else. That tells us something about the particle physics. So all is not lost if we only have gravity. And the piece of this that I'm particularly interested in is this one, the black hole merger bit, because the signature of that is really clean, right? Black holes are simple in the sense of the detector, their mass when you measure these events. And so, there is not a lot of messiness of understanding all the complex physics of these rich things. When you look at gamma ray signature from the galactic center, it could be astrophysics, who knows? When you look at this, it's really obvious what it was. It was a collision of black holes. And so there's a lot of signal there if you can pull out the physics. So let me just remind you, in all of that complicated picture, the part that's, kind of easy in some sense, is limits on when you can form a black hole. And basically, the gravitational collapse has to be able to win over all sources of pressure that would be sort of, pushing the matter or holding the matter apart. And if you think about exactly zero temperature, what is it that holds matter apart? And it's actually, quantum mechanics, the idea that you can't put two electrons in the same state. And so you can't have degenerate electrons. So that's called the degeneracy pressure. The fact that you can't push two electrons into exactly the same state means that you have kind of a pressure. And so gravity has to be able to win over that pressure. And if you sort of, assume that you've got some object that's neutral, that's made of electrons and protons, and the proton is much heavier, and we know its mass, this is the very famous Chandrasekhar relation, that black holes should be heavier than about a solar mass. Now, of course, the black holes that we detect don't form by purely cold gas that somehow just squeezes down into a black hole. They form in these very complicated nuclear physics processes. So you don't typically see a bunch of black holes that are a solar mass. So let's try to remove this complication, because it's really hard to predict from all of this picture what kind of black holes should be out there. And let's do something simpler. Let's say, well, that Chandrasekhar relation was pretty easy to calculate when I knew the mass of the electron and the mass of the proton. So what if we just stuck with that? What if we just stuck with an electron, a proton, and a photon? So something like electromagnetism. And if you go back to the Chandrasekhar relation, you find that if the heavy particle, that's not the proton, so this is new matter, it's a kind of dark matter, if the proton-like particle in the dark matter is heavier than our proton, the Chandrasekhar mass will go down, which means that, at least in principle, you could form black holes that are below a solar mass. And that's pretty cool, because you can detect those with LIGO. But if you see one, there's no way it came from astrophysical sources, right? You're not going to be confused as you are with electromagnetic radiation. It has to be something new. So it's a very clear signal. And okay, fine, that's a cute little relationship that's been known forever. But can you actually make those black holes? And again, if you have dark matter that has some kind of chemistry, you can. because you can have exactly the same kind of mechanisms to cool the dark matter and let gravity take over as you have in processes that form stars and black holes in the standard model. So if you have these cooling channels, you can get black holes dynamically from dark matter. And so inside a cloud like this, but made of dark matter, the gas has to cool to form compact structures. And the cooling story is exactly the same as it is in the standard model. A dark electron can hit a dark hydrogen. It can excite the dark hydrogen to some heavier state while the electron slows down. And then the hydrogen atom can release a dark photon. You'll never see. It doesn't matter. The point is the hydrogen cooled. And that process can go on until you can form compact structures. So I'm going to show you, as I'm coming to the end, I'm going to show you one thing that's kind of technical, but I wanted to just give you a sense of what this stuff looks like, when you do it beyond the cartoon level. And this is work that was led by graduate student Divya Singh here at Penn State. Really excellent work, and then also contributions from other graduate students, Michael Ryan McGee, and undergraduate Tosifa Akhtar, and with my faculty collaborators, Dongi Zhang and Chad Hanna. And what we did is basically say, well, LIGO measured a bunch of stuff, a bunch of black holes. And that gives a rate on how many sources are out, a limit on how many sources are out there. And you can use that to bound the number of black holes that could be made, say, of dark matter. And I say that because we're looking at objects that are less than a solar mass. And that can tell you a bound on the fraction of dark matter in black holes, because you know how much total dark matter there is as a function of the minimum mass. And so this red curve you can think of as the bound from LIGO on the fraction of dark matter that's in black holes as a function of the minimum black hole mass. And over here, there's no data, so we don't really have much of a constraint. And there were a couple of unusual events. And if you say, those were kind of interesting, let's assume that those were coming from dark matter black holes. Then, of course, you can put limits and you can say, oh, look, the fraction of dark matter in black holes must be this, and the minimum mass of the distribution must be somewhere in here. So why is that interesting? Well, it's interesting for the reasons we said before. If you find a black hole that's not coming from the standard model, and you hypothesize that it's coming from dark matter, the mass of that black hole tells you something about the Chandrasekhar limit for dark matter, which tells you something about the mass of a fundamental particle, right? Something like the mass of the proton. So you've turned a detection of colliding black holes into particle physics, in fundamental particle physics, in the sense that it tells you something about protons. You've also actually turned it into chemistry, because as we talked about, the black holes aren't just sitting there in an infinite cold vacuum forming right at the Chandrasekhar limit. They're forming in this messy thermal dynamical environment where chemistry matters. And so you can also say that the mass, the smallest black hole that you find, is limited by the smallest temperature the gas can cool to. And that temperature is given by these kinds of atomic and molecular transitions. So you've actually learned something about dark molecules just by detecting the collision of black holes. So that's the sense in which gravity is a chemist. So I just wanted to give you a picture of the people that have worked on this so you get a sense of how this science is done. These are the actual dark chemists here, graduate students, undergraduate students, and faculty. And I wanted to just take a minute and say these projects have been super fun, and they really happened because of having an environment where people just talk with each other and are able to talk about ideas that might be speculative or might be a little unusual, and do it in a way that focuses on the fun of doing science and isn't too grumpy, I guess. It's easy to be kind of grumpy about physics sometimes and worry that it's so competitive and it's so tough that we have to be really mean to each other about it. And we don't. And I think really great science and really fun science happens when we all sort of meet each other in an atmosphere of mutual respect and fun and excitement about the science. So try to keep that in mind as you go through the difficult times in your years of study. So let me just summarize and say, we have this universe that's extraordinary because it's so dynamic, right? It has this interesting large-scale expansion. It has these fascinating, really rich structures on small scales. We've learned an enormous amount from looking at light, electromagnetic radiation across the spectrum. And, one of the things we've learned is that our wonderful zoo is just the tip of the iceberg in terms of what's out there. And, we knew that from the minute we looked up at the sky, right? The minute you look up at the sky, you realize that what we see is a tiny fraction of all there is. And it turns out that most of the matter that's out there doesn't emit light. But that's okay, because in a hot and dynamic universe, we have other ways of finding out about the physics that's out there. And in particular, we have gravity. And the opportunity that's with us from these gravitational wave detections is just really remarkable. And I think we've only barely begun to see what it's going to do for us. So let me just finish by saying, I'll leave you with Fritz Zwicky and Vera Rubin. Zwicky first proposed, at least gets credited with proposing dark matter in 1933. It's been a puzzle ever since, and we keep thinking, oh, we're going to find it. It's just around the corner. It's just around the corner. And we haven't. So, maybe it's your generation, maybe by 2033, that we'll figure out what's going on here. Okay, let me stop there and I'll take questions.
Excuse me, ma'am. Hello?
Yes?
Hello, ma'am. Am I audible?
Oh, you're cutting out. You can try again, or you can use the chat maybe.
In the meantime, Anand, let's go ahead with your question.
Oh, yeah, first of all, Professor, I really enjoyed your talk. So thank you so much. And my question is, actually I have two questions, but my first question is basically about how, if we do, let's say at some stage, infer a standard model of dark matter, right, and we construct it, right? It still sounds like, at least based on what we know so far, that's going to be disjoint from the standard model of matter that we have right now. So what would a theory that in some sense merges these two pictures look like, right? I mean, I'm sure that we want something from which both of these would just be subsumed, right? So
Yeah. And I should say, we have amazing particle detectors, and we've certainly, people have had fabulous ideas for how to see if there are interactions between the dark sector and the standard model. But it's really hard to exhaust those possibilities. So, it could very well be that there's some interaction that's super, super, super weak, and it's going to be really hard to know what that limit is. Interestingly, the way you might combine these things comes back to the idea of cosmology again, because you really want a theory that says, why, when the universe began, did I have as much matter as we have, and do we have as much dark matter as we have? And what explains basically the temperature of each of those things at early times. And so, yeah, you'd like some sort of theory where there's some reason that very early in the universe, you got this population of dark matter at a certain temperature and standard model at a certain temperature in the amounts that we have, and why maybe they're not actually coupled, but they were still both created. So, I think we have a very little idea of how that might work. Sometimes people, more recently with the LHC finding only the Higgs, for example, and people wondering why the Higgs has the mass that it does. Sometimes people do postulate that there's a very weakly coupled but sort of rich sector of particles, including light particles, that can explain why the Higgs mass is the way it is. And those theories look different than theories that have been very popular for a long time, theories like supersymmetry, where mostly you're looking for new particles at higher mass. The idea of particles that are various masses, but very, very weakly coupled is kind of a new one. But you might think there's some theory motivation for explaining why, say, the Higgs has the mass that it does. But these are great questions, and these are things that will be occupying us for a very long time, I think. So you will get to work on this. Thank you.
Sorry, and I just had another question. This is related to strategy 1 for actually detecting dark matter, right? Which is through colliders. So do you think that we'll find anything new, not just in dark matter, but fundamental physics in general, if we just keep building bigger colliders on Earth? Or do we have to look beyond that, explore different classes of machines to actually, test things at really high energies?
Yeah, these are always fun questions, because what's great about all this is, you can think about all kinds of wild ideas, and the universe will happily tell you that you're wrong, 99.99% of the time. So, it's my impression that we'll see more progress in the next few years coming from astroparticle physics, together with gravitational waves, together with cosmology, than we might from terrestrial detectors. But I would be delighted to be wrong about that. So I really don't know, but I'm sort of betting by where I'm choosing to work on the astrophysics and cosmology side of it.
Thank you, Professor.
Yeah, there's a question in the chat. For a hypothetical matter, can we say dark matter exists in every galaxy? Like, is it a prerequisite for formation of a galaxy, or there are galaxies that exist without dark matter?
Yeah, great. Thank you. That's a great question. So I would say that, the more we look, the more we realize we don't understand things. And so, I think for a while it was sort of assumed that there might be typical, or not even typical, but universal amounts of dark matter in different types of galaxies. And that's really not the case. It actually turns out that when you look at, especially sort of small called dwarf galaxies, you find really, really large variation in how much dark matter there appears to be and how it's distributed in those galaxies. So we think the dark matter overall is essential for structure formation. It's essential for forming those first potential wells. But, the dynamics of what happens after that with hot gas and stuff that's colliding and stuff that's being blown out, we don't really understand. What's amazing is we know the Standard Model. You can make your little plush pillows of Standard Model particles, but that doesn't mean that we understand all of the effects that are out there from Standard Model physics in these really dynamic high energy environments. So dark matter distributions are very different. And part of what's interesting about that data is trying to understand why, and if it has to do just with Standard Model, or if it is telling us something about dark matter and potentially that it does have multiple particles that are interacting. So great question. I don't know the answer, but great question.
Professor, I had a question. You said that we have a general idea of how much dark matter we have in the universe and a rough estimate of how we can estimate the velocities of dark matter particles when they collide with our sensors. So would it be possible to create an estimated trajectory of in a place where the probability of finding dark matter is more, like the density of dark matter is more, and then actually placing the sensor there, which would give us more concrete results, or would it give us results sooner?
Yeah, that's an interesting idea. Yeah, so, I guess we sort of do that in the sense that when we look for signals, we look in directions where we expect that there is a lot of dark matter. We actually don't have a lot of ability to move complex instruments very far from our local location here on Earth. So we rely on the fact that some kinds of particles, escape their local environment very, very, very well and don't scatter very much, say, on their way here. Especially if they're particles that aren't charged, so they're not affected, say, by magnetic fields. So, we do use those strategies, absolutely. And when people think about looking for, new observations of dark matter, they indeed try to make sensitive instruments that will look very carefully in regimes where you expect, interesting structure from dark matter. But it's hard now to actually move an instrument physically to a very different dense region of very different density.
Good. Thank you.
So there's one question. Will there be any difference between the black hole and dark black hole except mass?
Yeah, great. Yeah, no, right. I mean, a black hole is a really simple object. That's part of why they're so beautiful and so easy, in some sense, to interpret the observations from. They're really simple. There's some ways in which you might think other factors about the black hole are different. So, for example, how many of them there are, as a function of distance out from us, which again is really a function of time. So you might think, depending on how black holes are made, you might find more of them, at different epochs of the universe, or more of them merging at different epochs of the universe in a way that's correlated with their chemistry. And maybe some other things, how they're spinning or what kinds of different masses are together in a binary object. But those are tricky right now. But, for the most part, just the object itself, they're the same. And that's sort of why this Chandrasekhar relation is so beautiful, because at least it's a limit where you do clearly have new physics and new particle physics.
Thank you. So are there any questions? Or if there are any other questions, then you can mail us and we will mail the professor and get it answered. So Shubham, do you have any question?
Yes, I have a question. Ma'am, as you said that there's no difference between a black hole and a dark matter black hole. So, I mean, with all the matter present in our galaxy, can it be it is possible that there are black holes which were formed from dark matter, but like they grew in size, and now we have no way of finding that if they were made from dark matter or from normal matter.
Yeah. And the interesting part of that question is there no way, or is there a way? And that's again this question of like how populations of these objects are formed and evolve. And we don't really understand that even for the standard model, but you might imagine a day in the future where we understand very well how many black holes and what their masses are and their distribution is from standard astrophysical channels. And we can understand those same questions for a dark sector. And we would find that those populations, even though they're both above a solar mass, they don't overlap. And so you can certainly try to do that modeling, and you can certainly go and look in the data and see if LIGO's detections are better described by what looks like one population or what looks like two populations. And those are interesting things. It's hard to be definitive with those things, but I think they're definitely interesting questions to pursue.
So there is one question by Soumyajit. Soumyajit, you can unmute yourself and.
Ma'am, as we know that beside dark matter, we have another thing called dark energy. So can you please say about that little bit?
Yeah, and this is an even more enigmatic question or problem, right? So absolutely. I mean, so when we look at that expansion history, we find that expansion rate of the universe today seems to be accelerating. So there's somehow something that's acting in a way that doesn't look like matter or radiation, and it looks like a constant energy density in the universe. And it's at a very kind of number that we don't understand why it's there and why there's that amount of that stuff there. And we really don't know. I mean, there are lots of papers and lots of things you can say about this, but we really don't know why that's there and what it is. And it's not obvious that it's connected to dark matter, except that both are, things that we don't understand. So they're dark in knowledge space, but it could be, and we don't know. So yeah, good questions.
So I think we can take this as a final question. So in reference to the Big Bang, could dark matter be what we call singularity? We hardly know anything about either of them, but do we see a sort of connection here? Like, we don't have a specific answer to that, but is it a possibility?
Yeah, maybe I'll say one thing. When cosmologists use the term Big Bang, they sometimes use it differently. If you track back the evolution of the universe that we see, and you assume that nothing was different except that things just sort of, as you go back in time, kept getting denser and more point-like, it looks like indeed a singularity. But another way of thinking about that is, as you go back in time, there had to be an event where a lot of energy was dumped into the standard model, and it got really hot to sort of start off the evolution of the standard model particles from hot and dense to cold and empty. And what we think is our best model of the universe so far is that there was this period called inflation early on, which was also a time of accelerated expansion. But you can seed from little fluctuations, you can seed the inhomogeneities in the density and the temperature that we see. And so if you put inflation there as sort of an origin for these fluctuations, then the thing you really want to explain is, how did you get this time when particles that we know became very hot? Basically, the energy that was in that accelerated expansion got dumped into the particles and made them very hot, and then things proceeded from there. Sometimes, it's maybe we can call that the Big Bang, because that was really when things got really hot and then started cooling. And it's really by that definition of the Big Bang that probably something connected with dark matter happened, because we have mechanisms for how this sort of energy density that's given us this inflationary period could be dumped into standard model particles and make them hot. But there may be a similar way that some of that energy gets dumped into dark matter and sets it at the temperature it's at, and everything evolves from there. But we don't know the right model for that yet. So sorry, hope that wasn't too long-winded of an answer.
Yeah, I think it answers the question. So if you have any other question, you can mail us at our email ID. The email ID will be given in the chat box. So I think we can conclude here. So thank you, Professor Sarah, for this insightful talk. It was amazing to see the images from Hubble telescope, and then how small our galaxy is in comparison to other galaxies which you showed. And I'm sure that the rotation curve, which like raised a lot of questions amongst the people, that might leave people a lot of to think offline and read about it more. And the journey of using different strategies, strategy one is mixed in the lab and everything, was also amazing. It was really beautiful. And I really like the analogy of the pet theory and the theory of like in physics, like how we create one and then we'll look for another one. That was really amazing, and I think it will stay for me for a long time. So I think it was a nice, yeah, like I thank you from the STEMS team for this wonderful session. And we all will meet on the third session of STEM 2022 lecture series, which will be an interview session of Professor Lisa Sorman at MIT. And it will be hosted by Anirudhan Ganeshram, who is the event coordinator of STEM. So we will meet on 30 September at 18 hours 30 minutes Indian time. And thank you once again, Professor Sarah, for your beautiful talk.
Thank you very much for having me. Thank you for your time. Bye.
Thank you, Sarah.